Welcome back to this video in which we want to discuss some topic modeling. More specifically, we just want to simply take a quick look at the LSA method, which stands for Latent Semantic Analysis. And I mean, there are definitely more approaches than we're discussing here. But to be honest, I just want to give you a short introduction into topic models or like popular topic models. Myself, I rather prefer like the word and document vectorizing models that we discuss later. But anyway, those models have proven that they can be quite useful for certain tasks. So let's just quickly take a look into them, okay? So in this video, let's just take a look at the LSA method, and you will find out that basically this is a method which is linear algebra processing of our document term matrices that we created before. Okay, so I mean, in general, there is the idea, when, as the name suggests, that topic modeling, that texts are marked by a certain topic in the text. So you can picture it like a newspaper, and like on a page at the newspaper, we may have a sports article, we may have a big article which is dedicated to politics or something, and I don't know, another article which is a gossip article or whatever. And so if we get a mixture of all the words on that page, some words may occur more often in a political context, some words may occur more often in a sports context, and so the idea is to use some topic modeling in order to have in the end generate vectors again for documents as well as for words, and especially with respect to the document specific vector, vectors which have similar topics, or document which have similar topics will have similar vectors here. Okay, and the LSA method, what it basically does, it further uses or processes the matrix the document term matrix that we observed before. And why do we do this? That's the first question, obviously. And I do not want to go too much into detail here, but as stated in the last video, or more or less in the video before that, if we would use a simple bag of word approach, for instance, then we have typically a very large matrix, because the first dimension is the amount of documents that we have. That usually is the lower number, or the smaller number, but the second dimension is the number of unique words that we have. And this is very likely, if we have a big corpus, something in the area or the range between 20,000 and 200,000. And so that's like the first thing. We have large dimensions. Large dimensions means a lot of data, a lot of things to process for your computer, for the methods we want to make use of maybe at a later stage, and so on. And also another problem is that this matrix from the bag of words approach is really marked by many zeros, and the zeros here, they do not really have a informative content, and but they are dominating the overall presentation of the data. Okay, and like I said, let's not go too much into detail here, but I think by intuition that already maybe tells us, okay, if mostly the information is zero, it may be hard for a method or a computer, whatever we're using it or how we want to call it, to really filter out the relevant part of the information. And this is why in many times the bag of words matrix, or also maybe the term frequency, inverse document frequency matrix, is further reduced, and reduced in a way such that in the end we all have lower dimensions again. I mean, you already know from our last sections like a little bit about dimensionality reduction, and what's done here usually is, as an input, we have the matrix, for instance, from the bag of word approach, and this matrix is then decomposed with certain techniques from linear algebra, and it's decomposed in a way such that the decomposition elements are lower dimensional. Okay, so this sounds complex and very theoretical, But in the end, let's just take a look what this means, and you will see that it's not so super technical, okay? I mean, like, okay. So we start with our matrix D here, okay? So it has a dimension n times D, and yeah, it is our, for instance, bag of word matrix. So we have, like, in each row represents a document, and the position for each column represents the number of occurrences of a specific word in the document. And what we're going to do is, for the LSA method, we separate this overall matrix into two other matrices with dimensions n times k and d times k. So that means, and if we have now k to be a small number, okay? So for instance, assume like d is 20,000 and k is maybe 10 or let's say 50, okay? Then of the overall information, which is, I don't know, let's say we have 1,000 documents, we have a 1,000 times 20,000 matrix. We decompose it into a 1,000 times 10 matrix. And still we have 1,000 rows, but now we have only 10 dimensions for each document instead of 20,000. If we would treat this first matrix as the matrix representing the documents, which will be the case here. And the other matrix, it is D times K, or it's transposed is K times D, that we can do matrix multiplication, but its original form is D times K. So the rows of that matrix are now representing the word vectors, so the columns originally in our data set. And like for each word D, we have D words overall. And for each word, we have a k-dimensional representation, and k is 10 again. Okay, so that is basically how we can come from a matrix that has dimension 1,000 times 20,000, and we separate it into two matrices. And the first matrix is here representing like the documents. So on a row-wise, on a row-wise observations. We still have for each row a document, but for each document now, instead of 20,000 numbers, we have 10 numbers or 15 numbers. So the number of k here is something that we specify, and if we want to have it really rather low dimensional, then we will set a value of k equal to 10 or something like that. Okay, and simply from coming out from the dimensionality. For each word here, we have, like in this transposed form, for every column still represents a word, but it only has again 10 values or k values that we need for each word. Okay, before that we had n values. Okay, each column we have n observations, and so as long as k is smaller than d and n, we have a dimensionality reduction regarding the first and the second matrix. I will show a quick example such that it's easier to picture all this, but first a few statements regarding the methodology. So you can see here there is no equal sign, because as long as k is smaller than the minimum value of d or n, it will not be possible to construct a decomposition which is exactly the original matrix. Okay, if we set k to the minimum of n or of d, so depending if n or d is smaller, then we can reach a perfect decomposition. But again, usually n and d are bigger numbers, so if we set k to a lower number, then we will not have a perfect recreation of the decomposition. Okay, so for the ones who are still wondering what I'm talking about, matrix decomposition in general is just we have an original matrix and it is decomposed into other arrays such as other matrices or vectors or combinations of matrices and vectors. But like if we if we calculate the product of those decomposed forms of the matrix, then in the end we'll get the original matrix. Okay, so we have such things as for instance, eigenvalue decomposition or singular value decomposition. But those are more or less all basic concepts of linear algebra. Obviously not basic for people like us, meaning not studying math or something, but for a math person, those techniques are really more like the basic and fundamental concepts, okay? What we have behind here is a little bit in analogy to the autoencoder. We are trying to have two matrices, and if we create the matrix multiplication out of them, the values at each position in the original matrix should be hopefully nearly identical. So basically, again, what we're trying is to have two matrices, and if we multiply them, they are supposed to be equal to the original matrix. And that is why this matrix factorization could be also stated as a minimization problem, in a way that search for two matrices with fictional values, right? Such that if their product is equal to the original matrix, okay? So, but that's not really the important part here, just that you know what this is. And K here is the amount of what we would call topics, okay? I forgot to mention that before, such that, there are no real topics like we would use topics in a real world setting. So we do not specifically say the first position stands for the sports part, the second position stands for politics, the third for economics or whatever. Those are like, fictional topics, such that for the moment we really do not have an idea what the real content of the topic is. But still, we imagine that some documents are more dominated by a certain, word usage than others, and this is represented by those topics here. Okay, good. So there are a few very interesting mathematical things, such as the orthogonality or orthonormal attributes. But basically, what you do not necessarily need to know, but what would be nice if you know it, that this problem can be solved by the technique of singular value decomposition. And for singular decomposition, as I stated before, we directly can get those two matrices if we would choose K to be equal to the minimum of N or D. And if we set K lower than the minimum of N or D, we're talking about a truncated singular value decomposition. And if we solve this, this is solvable, this problem here. But if we keep it like this, there is no unique solution here. Okay, so we will find many different solutions for those two matrices. In order to have really a unique solution, what usually is further done is to normalize it, like as it's stated here. I mean, this is quite formal and you do not necessarily need to go through it. I just wanted to share the information with you. This is just how we would, generate unique representations, and that's important, I think, because unique means that we're ending up more or less at the same page regarding the representation of document and word vectors once we do this. And non-unique would mean we have, every time we do this with the same set of data, we have completely different and new vectors for documents and for the words. And this is obviously something that we do not want to have, so we have some form of normalization here, okay? But basically, that's just a further decomposition, which makes sure that we have some, unique solutions here, okay? So, I mean, I'm guessing this really sounds all very formal, so I tried one more time to keep it simple, okay? So, assume we are here in an example with our 5 sentences, and now let's pre-process them. So we would have it like this here, okay? And you know this from before, so we use the count vectorizer, and this is like our document term matrix that I was referring to. So each row here represents the document, so in our case a sentence, and each column represents a word. Okay, but the numbers here are the important part because that's our matrix that we're using, and that's our original matrix that I will have D here. And now we want this kind of decomposition. So without any knowledge, without the need that we need to know by ourselves how to exactly do this, we could use for instance, the singular value decomposition function from the SciPy package. It's even implemented for sparse data, so that what I'm doing here is not necessary, or it's not really necessary, but we can do this. And we need just to import the NumPy library here. And then what this does is exactly what you see here. Okay, so this decomposition. And now let's take a look at this first matrix that we get here. So those are those values here, and in the beginning we have here those 5 rows and this information as you see here, and after the decomposition we have now for each document a vector. Okay, and maybe we can make a quick check. So let's take a look at the original sentences. We have here machine learning is so interesting. And I don't know, maybe I'm not really sure. Or okay, these last 2 sentences, the coffee machine is broken and coffee machines are interesting to study. They are quite similar. So let's check it out. I mean, I'm not really expecting that this works here, but even a little bit it seems to work, because as you can see here, at least like those have negative values here, and I would say also in absolute terms the largest negative values. And for instance, the second sentence would look similar, but not so large negative in absolute terms. So let me take a look. And this makes really sense. I'm quite surprised that it works so good, at least even though for this very, very small example, because we have here something with coffee, we have here something with coffee, and we have here something with coffee. And if you take a look, everywhere where we have something with coffee, we have 2 negative values. Okay, so meaning somewhat, even at this very small example, the decomposition just needs 2 dimensions in order and still retains some characteristic here. Okay, and I mean, if you re-execute this many different times, let's take a look how stable that is. You get new numbers here. To be really honest, I'm not sure why they are so different. I mean, as I said, okay, maybe that's okay. Do not worry. I mean, it's still very likely the same if you're not multiplying it with the singular values. Let me quickly check this out. Okay, I think it's supposed to do this. Okay, because what I'm using here for the document representation is the product of this here, and that's how one is supposed to use it. Okay, and yeah, and anyway, what's happening here is, as you can see here, take always a look at the second, the fourth, and the fifth. They always have a very similar shape, and those are the 3 sentences which deal with coffee. But as I said, okay, now we get always the same results, and that's how it is supposed to. Okay, just the sign changes sometimes. Okay. Because obviously this is depends on, there are different algorithms which can be used to solve this here, and yeah, but it's okay. So as long as the relationship here stays the same is fine, but if you use the same algorithm, it always should lead to unique representations of the documents and the word vectors themselves. And I mean, we can check out the word vectors. So that would be for our third word, it's 2-dimensional representation. And our third word is coffee again, or I don't know, do we use let me just take a look. I think I'm using the non-stop word matrix here because I only initialized that one. So it would be and. Let me just put that together. Let's check out what happens if we now switch to this matrix, so without the stop words. And to, okay. Quite interesting. I'm just looking at, like, again, second, fourth, and fifth here. And I mean, it still kind of keeps its relations. To be honest, I'm really not sure why sometimes it's changing and sometimes not. I'm not too deep. My knowledge here is limited as well, but I find it quite amazing that it works here in this example better with the stop words. Anyway, I mean, this is a very unrealistic corpus, and in reality, if we have a larger amount of documents, it shouldn't be that unstable numerically, okay? Anyway, just what I wanted to say originally is, like, if we have 2 dimensions here, so I can set this also to 4, for instance, and then we would have like a 4-dimensional representation of each document. And each instance here, so that value is what we would refer to the value that corresponds to the first topic in that representation. That is the value that corresponds to the second topic in that representation, and to the third and to the fourth. So we actually do not have any idea what the topics are here, but we assume, let's go back to 2, that if the document content is similar, then this topic-like realization is also similar if it works well. And I mean, we then could check for vectors, for documents that are similar to each other based on that representation. And we could look, for instance, for words that do maybe often occur in that in those topics and those documents, and words that do seldomly occur in those topics. And then those words could give meaning to the topics, or we should probably are supposed to do this. Maybe there are better ways to do this, but let's just stop here, because actually that was not the important part what I wanted to share with you. So I mean, I'm absolutely aware that this can be quite confusing. So let me just roll this up one more time. Okay, so in the beginning, we have a matrix that is quite large, usually with respect to both dimensions, and that has many zeros or is dominated by a value of 0, which makes it usually, or for some methods, makes it hard to learn something from. And that is why one tries to reduce the dimension of a word or of a document representation, or basically we're doing both at the same time. And this is achieved by a mathematical technique which is called matrix decomposition. There are different forms of matrix decomposition. The one that is used for the Lsa method is a singular value decomposition, which is specifically a truncated singular value decomposition. So we try to decompose the original matrix into 2 smaller dimensional matrices, where one represents the document vectors and the other represents the word vectors. And the smaller the dimension we choose here with respect to the value of k, usually the more difficult the exact, or the more difficult it will get for the model to regenerate the original values perfectly, but the better or the more is the original dimensionality reduced. And the word, or the numbers that occur here, they do not make any sense. They are kind of fictional. But what should make sense is that now with those lower dimensional representation of a document or of a word, still we would hope that if a similar set or similar mixtures of words are used within a certain subsample of documents, then we would expect that those documents have similar document vectors even in their lower dimensional representation. Okay, this is more or less the idea. In the next video, we're going to LDA, which stands for latent Dirichlet allocation. It is actually a completely different approach, and from my opinion, it's at least has I would say, a more direct access regarding really topic, like the modeling of topics, the idea that a text is maybe a collection from different topics, and different words are maybe used like more or less often regarding a certain topic we have. But let's discuss this in the next video, and see you there. And as I say, stay tuned and stay excited, because in my opinion, the real interesting applications are coming in like the video after the next video. Even though, watch the next video. See you there. Bye bye.